Welcome to today's paper reading. Today's paper is titled SelfGoal. Your language agents already know how to achieve high-level goals. This paper, titled SelfGoal, Your language agents already know how to achieve high-level goals, was authored by Ruihan Yang and colleagues from Fudan University and the Allen Institute for AI. It is currently under review for publication. Language agents, driven by large language models, are increasingly utilized as decision-making tools in fields like gaming and programming. However, these agents often struggle with achieving high-level goals without detailed instructions and in environments with delayed feedback. This paper introduces SelfGoal, a new approach designed to improve agents' ability to achieve high-level goals with limited human input and environmental feedback. SelfGoal works by adaptively breaking down high-level goals into a tree structure of more practical subgoals during interactions with environments, identifying the most useful subgoals, and progressively updating this structure. Experimental results show that SelfGoal significantly enhances the performance of language agents across various tasks, including competitive, cooperative, and environments with deferred feedback. The advancement of large language models has enabled the creation of autonomous language agents capable of solving complex tasks without specific training. These agents often face challenges due to the ambiguous nature of high-level goals and the impracticality of frequent retraining. Previous methods have focused on either pre-task decomposition or post-experience summarization, but these approaches lack empirical grounding and effective strategy adjustment. SelfGoal addresses these issues by dynamically decomposing tasks during interaction with the environment, using a tree structure for hierarchical guidance and adaptive self-growth. This framework ensures that agents can consistently achieve high-level goals without the need for retraining. In the related work section, the focus is on three main areas. Firstly, learning from feedback, where language agents are enhanced through feedback from environments. For instance, reflection allows agents to reflect on failures and devise new plans, while Voyager develops a skill library from feedback in Minecraft. Secondly, LLMs for decision-making, where large language models are used as policy models in various interactive environments. However, these models often struggle with high-level, long-term goals and require additional support. Thirdly, decomposition and modularity, where complex tasks are broken down into subtasks to enhance task-solving capabilities. Approaches like hierarchical task networks simplify problems using domain knowledge, but there is a need for more dynamic, grounded adjustments during interaction with environments. Figure 1 provides an overview of the SelfGoal framework, using a bargaining example to illustrate its operation. The agent interacts with various environments, making actions based on both environmental feedback and the GOLTRE. The GOLTRE is dynamically constructed, utilized, and updated through two main modules: the search module, which selects the top k most suited nodes of goals based on the current state and existing nodes in GOLTRE, and the decomposition module, which breaks down goal nodes into more concrete subgoals, ensuring an adaptive self-growth of GOLTRE. This dynamic approach allows the agent to effectively achieve high-level goals in diverse environments. SelfGoal is a non-parametric learning approach designed to help language agents achieve high-level goals by decomposing them into specific subgoals. This top-down hierarchical decomposition is represented as a tree structure, known as GOLTRE, which guides decision-making. The framework consists of three key modules: search, decompose, and act. The search module identifies the most appropriate subgoals for the current situation, while the decompose module refines the GOLTRE to adapt to the environment. The act module updates the instruction prompt for the language model and takes actions based on the identified subgoals. The algorithm workflow involves initializing the actor and policy, generating the initial GOLTRE, and iteratively updating it until a stopping criterion is met. The experimental setup involves evaluating SelfGoal across 4 dynamic tasks: public goods game, guess 2/3 of the average, first price auction, and bargaining. These tasks are implemented using existing frameworks such as Gamma Bench, AUC Arena, and Deal or Not Deal. The tasks are either single-round or multi-round games, requiring collaboration or competition among multiple agents. For agent frameworks, The study employs task decomposition methods like react and adapt, and experience summarization methods like reflection and CLIN. The backbone language models used include GPT 3.5 Turbo, GPT-4 Turbo, Gemini 1.0 Pro, Mistral 7B, and Qwen 1.5. The evaluation metrics vary by task. For the public goods game, the score S1 is calculated as the average contribution. For guess 2/3 of the average, S2 is 100 minus the average choice. For the first price auction, S3 is the true skill score, and for bargaining, S4 is the absolute difference in profits divided by the number of items. Table 1 categorizes the tasks studied in the evaluation of SelfGoal. The tasks include the public goods game, which is a cooperative single-round game. The guess 2/3 of the average is a competitive single-round game. The first price auction is a competitive multi-round game. These tasks require different levels of collaboration and competition among agents, providing a comprehensive test of SelfGoal's capabilities in dynamic environments. Table 2 presents a comparison of the SelfGoal framework powered by various models against alternative methods across 4 distinct scenarios. The data highlights that SelfGoal consistently achieves superior results, with larger language models demonstrating higher performance gains. Notably, SelfGoal's ability to dynamically adjust contributions based on observed behaviors and token distributions in the public goods game exemplifies its effectiveness. This table underscores SelfGoal's advantage in overcoming the limitations of traditional task decomposition and experience summarization methods. The main results show that SelfGoal significantly outperforms all baseline frameworks, especially in environments with high-level goals. Larger language models, LLMs, tend to produce higher gains. However, task decomposition methods like react and adapt often provide subgoals that are not suited for the current situation, leading to broad and meaningless guidance. In contrast, SelfGoal dynamically adjusts subgoals based on the evolving game's situation, aligning with the main goal. This approach not only improves performance but also shows superior results in smaller LLMs due to the logical structure of the GOAL tree. In auction competitions, SelfGoal's strategy involves frequent bidding in the early stages to secure high-priority items before competition intensifies, unlike other methods that tend to be overly cautious. Table 3 presents the results of auction competitions between 5 agents using various frameworks, including our SelfGoal. The data reveals that SelfGoal significantly outperforms the baseline frameworks in these competitive settings. Specifically, other methods exhibit overly cautious bidding behaviors, often ceasing to bid or avoiding participation once the bidding starts, leading to zero profits. In contrast, SelfGoal adopts a strategy of frequent bidding in the early stages of the auction, enabling the acquisition of high-priority items before competition intensifies in later stages. Figure 2 illustrates the impact of varying the threshold psi on the granularity of subgoals and SelfGoal's stopping mechanism. The performance of the agent initially improves as the depth of the subgoals increases, providing more detailed guidance. However, this trend reverses as the depth becomes too great, likely due to the interference of repetitive guidance, which complicates the selection of useful guidance. This suggests an optimal level of granularity exists, balancing detailed instruction with practical utility. Figure 3 presents an ablation study comparing different search modules in SelfGoal. The LLM-based search module, instantiated with GPT 3.5, achieves a better score in both auction and bargaining games compared to random selection and embedding similarity methods. Notably, the embedding similarity method underperforms random selection in bargaining, likely due to the brevity of guidance making it difficult to capture semantic embeddings between subgoals and situations. This study underscores the rationality of incorporating an LLM-based search module in SelfGoal's design. Figure 4 presents an ablation study comparing the performance of GOAL tree generated by GPT-4 and GPT 3.5. The study reveals that GOAL tree from GPT-4 significantly enhances SelfGoal performance, achieving gains of plus 2.87 in auction and plus 3.10 in bargaining compared to GPT 3.5. This improvement is attributed to the superior guidance provided by GPT-4, which leverages its enhanced understanding and summarization capabilities. Figure 5 illustrates the patterns of model behavior in repeated games. In the public goods game, A, the agent equipped with SelfGoal exhibits more rational behavior, consistently contributing fewer tokens to achieve a Nash equilibrium compared to other methods. In the guessing game, B, SelfGoal demonstrates enhanced theory of mind, TOM, abilities by converging to a guess of 0 more quickly in each round. These results highlight the effectiveness of SelfGoal in improving both rationality and TOM capabilities in model behavior. Figure 6 illustrates the effectiveness of SelfGoal in a bargaining task using Mistral 7b. Clean and Adapt provide either overly broad or overly detailed guidance, leading to significant profit discrepancies. In contrast, SelfGoal offers actionable guidance, such as asking clarifying questions and making concessions, which helps agents propose plans that minimize profit differences. This results in more successful negotiations and reduced profit discrepancies. In this paper, the authors introduce SelfGoal, a framework designed to enhance the capabilities of large language models, LLMs, in achieving high-level goals across various dynamic tasks and environments. SelfGoal significantly improves agent performance by dynamically generating and refining a hierarchical GOL tree of contextual subgoals based on interactions with the environments. Experimental results demonstrate that this method is effective in both competitive and cooperative scenarios, outperforming baseline approaches. Additionally, the GOL tree can be continually updated as agents with SelfGoal further engage with the environments, enabling them to navigate complex environments with greater precision and adaptability. However, the authors also note that while SelfGoal is effective for small models, there is still a demand for the understanding and summarizing capability of models, which might prevent SelfGoal from achieving its full effectiveness. Thank you for watching.